Okay, good morning, everybody. It's my pleasure today to present you some of the key comparison results that had been taken place in the inorganic analysis working group and are in close context to the monoelemental solution business. But before I start with the actual topic, I'd like to remind you that 2019 is a very special year for chemists and especially for metrologists, as we have a lot of events to celebrate. We celebrate the 150th birthday of the periodic table. And furthermore, upcoming next month, the revision of the SI, which is, of course, of high importance for metrology. And also, last but not least, today we are here to celebrate the 25th meeting of the CCQM at BIPM. And why do I mention this? The three events all play an important role in the topic of monoelemental solutions. So they kind of form three pillars that are important for achieving the highest level of accuracy. Of course, we need some elements that we choose from the periodic table to start with the solid materials usually and form our solutions thereof. And we have a high interest to link them to the SI, of course, to make them traceable. And this can be achieved on the highest level of accuracy, I think, by using the platform that CCQM provides. Because here we can compare our results with experts from all over the world, and we can gain more information on how to improve our results and make them comparable all over the world. For those that are not so familiar with the numbers, like I am still, I put in the elements that were treated in different comparisons, and you can see that we have three groups of them that represent main capabilities that are tested within the comparisons. And today I will focus on those that deal with the purity determination on the bottom, and some examples from the precision measurements on the top. But before I go even one step above the precision measurements, and I'd like to start with an example from a very early key comparison. And here we had a real-world sample with a natural matrix. The samples were natural water from this nice river here, from the Clear Creek River in Colorado, US. And the task was to determine cadmium and lead in these river samples. At first glance, you might think that the comparison worked out quite well, because all of the results within the limits of uncertainty include the median value. But when we look at the scale on the right-hand side, we can see that the relative deviation show a large spread. It's almost 8% or something. So it was not entirely satisfying, this result, as we had a presumably easy matrix and easy elements that we were looking at. And so the question came up, how can we improve these results? Especially when we look at the methods that were used, because all participants used the same method, IDMS, and so the results were expected to show a smaller spread. So only shortly after this key comparison, the community went one step back to the precision measurement capability, and EMPA and LNE provided monoelemental solutions for four elements that you can see on the left-hand side. And now the participants' task was to measure the given samples against a standard of their choice. And you can see on the right-hand side at the relative scale that the results were now much closer and the spread was much lower. And even if we look at participants that just joined in the game for the first time, even there the spread was not as large as it was in K2 before. So a few years later, in 2010, a similar key comparison was conducted, and this one was hosted by PTB. They sent some samples around. This time they used other elements which were chosen due to different features. For example, cobalt was chosen because it's a monoisotopic element, and lead due to the difficulty that usually you have to determine the isotope ratios because it has a natural variation in it. And again, here we can see the number of participants already increased, which is really nice to have more and more institutes joining in. And also when we look at the core results, the spread again decreased. And so the next sample I'd like to show is something that now increased the difficulty again, because here we used a matrix that consisted of 15% salt. So it was already the follow-up study of another comparison before where the salt was shipped to the participants. In this case, the solutions were shipped. And there were several tasks to perform. 3 anions had to be measured and 1 mass fraction of a cation, which I present to you here in this picture. It was lead again. And also, I think the isotope ratios had to be determined. And here you can see that the spread on the relative scale increased again. But please keep in mind it is really due to the very difficult matrix. You have to do matrix separation to determine the lead correctly, and the lead is on the same concentration level as it was in the river water example, so it was a low concentration level. And nevertheless, the participants really performed well, and we can see that the performance overall increased a lot. And the same holds true for my last example for the CCQM studies. It was the purity determination within a metal. Zinc was chosen due to its relevance in industry and its overall relevance. And the participants were free to use whatever method they liked to determine the mass fraction of zinc directly, for example, by titration, or indirectly by summing up all the impurities and subtract it from 100%. And this is quite a difficult task too, and you can see that here, even on the right-hand side on the scale, the participants really did a great job. They improved again their results, and we're really happy to have this overall improvement of the participants' capabilities. So you can kind of say that from the year 98, when K2 started, up to more recent comparisons, that we increased the overall performance by roughly 3 orders of magnitude, which I think is really good. Still, when we have a look at all the elements that are in close contact with the monoelemental solution business, also including those that were tested as starting materials and the purity of those, there are large gaps. Of course, it's maybe not necessary to test every single element because you can group some of them, but still there's a lot of work to do. And also the question arises, how important is this work for the outside world? And of course, it's of high importance. We've heard it already. And I chose one example where you can see that it affects almost every one of us when it comes to medicines and medicinal products, because on international level, the ICH Q3D, that's a guideline set up from the International Council for Harmonization of Technical Requirements for Pharmaceuticals for Human Use. And it now regulates, since a few years, that elemental impurities like mercury, lead, cadmium, arsenic have to be analyzed with modern instrumental methods, and therefore you are in need of reference solutions. And due to this reason, the European Directorate for the Quality of Medicines in Healthcare, EDQM, came to PTB and BIPM and asked if we would be willing to join a project under their lead where SI-traceable reference solutions should be set up for 24 elements. The concentration level should be 1 milligram per gram, and the whole thing should be in support of the European pharmacopea. Later on, also the JRC and GIL joined this cooperation, and they are supporting the three partners with the implementation of the reference standards. So when finally in 2018 the new guideline was implemented into the European pharmacopea, it was becoming legally binding for all the member states of the European pharmacopoeia, and at the same time the elemental impurities reference solutions became available at the EDQM for the first 4 elements. And in the during the development with measurement techniques for these elements on these high concentration levels, we faced the problem that we had to find out which method is best suited to measure mercury on such a high concentration level. Of course, at first sight, you would think that you would like to choose ICP-MS, but of course, then you have to dilute your sample several times. You need an expensive spike material if you want to, not to lose information during the dilution processes, and this was simply out of reach for us. So we decided to use a slightly modified ICP-OES approach, where we only had one dilution step, and by using an internal standard and the bracketing method that was already used for other elements before, we were able to achieve very good results, and even better than we had expected them to be. So we could not differentiate the gravimetrical value for the mass fraction of mercury from the measurement value within the uncertainty of the measurements. And furthermore, the given expanded measurement uncertainty of 0.16% does not only include the measurement uncertainties, but also includes the homogeneity of a large batch that we tested, and furthermore the purity of the primary reference material. So we're really happy to had this outcome, better than expected, and this is just an example to show you that monoelemental solutions and the technical developments that go along with it are still of high interest, and we are about to publish these results. And with this, I'm at the end of my talk, and I'd like to say that there is still a lot of work, not only different elements, but also the focus on non-metallic impurities, difficult to dissolve metals and oxides, things that we have learned are already on the 5-year plan of the inorganic analysis group, and which will be dealt in the near future. It's always an issue to decrease measurement uncertainties for existing methods and to, like in the Mercury case, maybe extend the concentration levels to unusually high or even normally on the lower side. And one important thing would also be to develop methods and instruments further to make them really SI-traceable, for example, the laser ablation systems. So in the end, after 25 years of CCQM, this is just the beginning. Thank you.